excursion, we visit a museum, temple, cliff, we watch sunset together, and yesterday we had a day off. So I hope that you had enough rest and regain your energy to start your day and to continue with this course. And do not forget that last week you got some problem set to solve, because tomorrow is 23rd of July, the last day to submit the task. It's not too late to finish the task as soon as possible.
To all participants, we have an information for you that starting from today, we don't need to walk to UZ Cafe and Resto for lunch, because we will have our lunch together in this room. Not buffet, but lunch box.
No buffet, no buffet.
So we can start the third session earlier at 1:30 p.m., not 2 p.m. Okay, are you ready to start the course? The first session is Introduction to Secret Sharing, which will be delivered by our honorable speaker, Dr. Romar de la Cruz. Please give him a warm welcome and a great applause. To Dr. Romar de la Cruz, may I invite you to come to the stage. Thank you.
Good morning to everyone. First of all, I would like to thank the organizers for inviting me to give a talk here. So it's an honor to be here in front of you. Now, I was tasked to talk about secret sharing schemes. So it's a cryptographic protocol. So, so I have two chances to give a talk. So the first part of my talk, my objective is to give an overview of the theory of secret sharing. So for the first part, this is the outline of my talk. So first, I'll discuss the basic concepts in secret sharing, and then for the next few topics, I will talk about the connections of secret sharing with other objects in mathematics and computer science. So you will see some of the tools and techniques that are used to study secret sharing. Then the next part, the second part of my talk, so after the break, I will focus on the connection between secret sharing and error correcting codes. So I guess you're already familiar with error correcting codes. Okay, so to start, so I decided to present the original motivation for secret sharing. So it was introduced in 1979 to address this problem. So basically the problem is, how do you protect cryptographic key? So when we say cryptographic keys, I think you're familiar with, for example, encryption, decryption, right? So they use secret keys for encryption. So there was this problem in cryptography. How do you protect those keys? So how do you secure them? How do you store them in a secure way? So we look at some options for safeguarding cryptographic key. So the first one is, yeah, you're familiar with this. You create multiple copies of the key. So say n copies, and then you store them in, of course, different locations. You don't store them in the same location. Now, let's evaluate this option in terms of these two criteria. So security and reliability. Okay? Let's start with reliability. When I say reliability, so it means that it's easy to recover the key. So can you always recover the key? For this one, it's reliable. Because you have n copies, you just need one of the copy. So you have the key. So in that sense, it's reliable. Okay? Now, second criteria is it secure? Do you think it's secure? Actually, it's not. Because if you have an attacker, you just need to attack one of the copies. So if he gets hold of one of the copies, he already knows the secret key. So in that sense, it's not that secure. Okay? So the next option is, you're also familiar with this, you split the secret into, let's say, n pieces. So in such a way that you need all the pieces to recover the key. So let's evaluate, is it secure? That option, second option. That one is secure because to recover the secret key, an attacker needs to get all the pieces. He needs all the n pieces. As compared to the first one, he just needs one of the copies of the key. Now, is it reliable? It's not that reliable because if at least one of the pieces is destroyed or got lost, so you cannot recover the key anymore. So in that sense, it's not that reliable. Okay? So in 1979, so Shamy and Blackley, independently, they proposed the following solution. So what you have is something in between those first two options. So you split the secret into n pieces in such a way that to recover the secret, you only need t, which can be less than n, of the pieces to recover the secret. So you will see this option, it will provide some form of security and some form of reliability, which is better than the first two options. Okay, so let's start with the following. The usual entities in a secret sharing scheme. So we have a dealer. So the one who has the secret, it's usually called the dealer. And then we have a set of n participants. So we denote it by p sub 1, p sub 2, up to p sub n. And then we have this special collection of subsets of participants called the access structure. So later on you will know why it's called the access structure. So this is an informal definition of a secret sharing. Later on I will give a formal definition, but it's good to start with this one. So you will get the main idea of a secret sharing scheme. So a secret sharing scheme for, so this is the access structure gamma. So it's a method to distribute shares to each of the participants in such a way that these two properties are satisfied. So any subset of participants in the access structure can determine the secret. So that's why it's called the access structure. So the elements of the access structure are the subsets that can recover the secret. Okay? Now, the second property is if a subset is not in the access structure, then they are not allowed to determine the secret. So basically, that's the main idea of secret sharing scheme. So some of the applications, so as I have mentioned, secret sharing schemes were proposed originally to safeguard the cryptographic keys. But as of now, it is also used to construct other cryptographic protocols. So some examples are, this one is oblivious transfer, private information retrieval, and then you also have the multi-party computation. So some examples of cryptographic protocols that uses secret sharing schemes. In the second part of my talk, I will describe MPC, how secret sharing is applied to MPC. Okay, so now we discuss the Shamy threshold scheme. So this is the first secret sharing scheme that was proposed. Shamy is, if you're familiar with Shamy, the guy in the RSA, so it's the same, Shamy. So it uses polynomials over finite fields. Okay, so the idea is simple. So the dealer, if you remember, the dealer is the one who knows the secret. So first step is he chooses n distinct non-zero elements of finite field, FQ. So let's denote those elements by x of I from 1 to n. And then he constructs this polynomial over FQ. So A of x. So the polynomial, the degree is at most t minus 1. And then observe that the secret is the constant term of the polynomial. Now, using this polynomial, the dealer computes the following. So he evaluates the polynomial. The dealer evaluates the polynomial. And then the evaluation is given to p sub I. So for example, for p sub I, so you have a of x sub I. So the x sub i's here, they correspond to the participants. Okay? So the participants are given evaluations of the polynomial or points in the polynomial. Okay, so so let us take a look if it satisfies the properties of secret sharing scheme. So suppose we have a subset of participants, B. Now, if the size of B is at least T, so you have at least T participants, so recall that they will have at least T points of the polynomial. Then the polynomial is of degree at most T minus 1. So you have T points of a polynomial of degree at most T minus 1, so it's enough to recover the polynomial. By, you can use Lagrange interpolation, or you can just use a system of equations to determine the polynomial. So they can determine the secret. Now, if the size of the participants, the subset of participants is less than T, so what do they have? They have, let's say they have T minus 1 points of the polynomial. But the polynomial is degree at most T minus 1. So they need one more point of the polynomial. Now, what they have is actually, so they can guess for the other point, but for every guess that they take, it will result to a unique polynomial. Okay, so what happens is, they can only guess for the secret. So in other words, we say that they cannot obtain any information about the secret polynomial. So this is an example of what we call T out of n threshold scheme. So the access structure, the sets that are authorized to recover the secret are the subsets of size at least T. So that is the access structure of the Shamy threshold scheme. Okay, so now let's define more formally So going back to the access structure, so this is the collection of subsets that can reconstruct the secret. And then an element of the access structure is called an authorized set. Now, the access structure, you will observe it has this property. It's called monotone increasing. So it's straightforward. If you take a set in the access structure, and then you take a set containing that element of the access structure, then obviously it must be in the access structure. Okay? So because they already have enough shares to recover the secret. So this implies the following. The access structure is determined by this set called the minimum access structure. So basically the elements are minimal sets, minimal authorized sets, minimal with respect to set inclusion. Okay, so this is the minimum access structure. Next, we define the privacy structure. So we denote this by delta. So these are the subsets that cannot obtain any information about the secret. So we call it the privacy structure. So an element is called a forbidden set. And then similarly, it satisfies monotone decreasing. So if a set is in the privacy structure, any subset will also be in the privacy structure. So it cannot recover the secret. And then, so we also have this. Privacy structure is determined by the, this time, the maximal elements. Maximal with respect to set inclusion. So an example to illustrate this concept. So for the Shamy T out of n threshold scheme, so we already seen that the access structure is so the set of subsets of size at least T. So the minimum access structure, the minimal authorized sets, are the subsets of size exactly T. And then the privacy structure, subsets of size at most T minus 1. And then the delta plus will be the subsets of size exactly T minus 1. Okay, so to give a formal definition of a secret sharing scheme, we need Shannon Entropy. Okay, so I'll just define this one. So you have a random variable x with probability function p of x. So the Shannon entropy is denoted by h of x, so it's given by this. So logarithm is base 2. You can think of the Shannon entropy or the entropy of x as the it is the amount of uncertainty of the random variable. Okay, so now we can give a formal definition of secret sharing. So we will need the following notation: S be the set of all possible secrets, and then S sub I is the set of all possible shares for participant P sub I. Now we represent a secret sharing by a mapping sigma. So it's a mapping from the set of secrets going to the shares. So you have the secret, and then the output are the shares. R here is the set of random strings. So you apply some randomness to the secret. So this is a formal definition of secret sharing using entropy. So you have access structure, privacy structure, and then so sigma is a secret sharing scheme realizing gamma and delta, provided the following properties are satisfied. So the first property is for every authorized set A, we have the following. So the entropy of S given S sub A is 0. I have to explain the notation. S here is the random variable corresponding to the secrets. So the S sub A, this is the random variable corresponding to the shares of the set A. Okay, so one way to interpret this, so H of S given S of A is equal to 0, it means that they can recover the secret because the amount of uncertainty is 0. So they can recover the secret. Now, the second property, so for every forbidden set A, so they cannot obtain any information about the secret. So it's equivalent to this one. So this entropy is equal to the original entropy of S. So it means they cannot obtain any information about the secret. So if you recall the informal definition, this is a formal way of stating those two properties. Now, so some terminologies related to the security of a secret sharing scheme. So we say that a secret sharing scheme is perfect if we have the following. So the privacy structure is the, I think there's a mistake in the notation. It should be 2 raised to P. It's the complement of the complement of gamma. Okay, so it means that if you have a perfect scheme, if you have a subset of participants, so it's either in the access structure or in the privacy structure. So either they can recover the secret or they have no information about the secret. So that's what we mean by perfect. So otherwise, non-perfect scheme. Now, what do we mean by a non-perfect scheme? So you can have subsets unauthorized, so not in the access structure, but they can get partial information. So something in between. Now, we also have what we call unconditional security and computational security. Perhaps you're already familiar with these two terms from cryptography. So when we say unconditional security, so it means that the security of the scheme is independent of the computing power of the adversary. Now, computational security, it means, well, one way to describe is the security of the scheme depends on some difficult problem. For example, factoring or discrete logarithm. So that's one way to describe computational security. For my talk, I'll just focus on the schemes with unconditional security. But there's a large body of research on secret sharing with computational security. Okay, so after security, we have what we call the information rate. So this one is a measure of efficiency of the scheme. Similar to the, for an error correcting code, you have the rate of a code, right? So it's similar concept. So the information rate of a secret sharing scheme is defined as follows. So it's denoted by rho of sigma. So it's the minimum of this h of s over h of s of I from 1 to n. So if you remember, this one represents the secret, h of s, and then h of s of I represents the size of the share. So one way to look at the information rate is you have the size of the secret over the size of the share. So that's one way to look at information rate. So it measures the ratio of the size of the secret over the size of the share. Now, we have the following important result for perfect schemes. So perfect schemes, if you have a subset of participants, so it's either it can recover the secret or it doesn't have any information about the secret. So it has this property, the size of the share is greater than or equal to the size of the secret. So if you want perfect security, you cannot avoid this property. The size of the share will be greater than or equal to the size of the secret. So for perfect schemes, because of the previous theorem, the information rate is at most 1. It will be at most 1. So we call a perfect scheme ideal if the information rate is the maximum value, which is 1. Now, an open problem in secret sharing is the following. So you determine the ideal access structure. It means that these are the access structure that can be realized by ideal perfect scheme. So it's still an open problem. Now, if you have a non-perfect scheme, so you can have information rate that is greater than 1. Okay, so what we have here is there's a trade-off between security and efficiency. So if you want perfect security, it's less efficient. If you want non-perfect security, you can be more efficient. So there's a trade-off between security and efficiency. An example is again, the Shamy T out of N threshold scheme. So it is perfect, and at the same time, it's ideal. So if you remember, in the Shamy threshold scheme, the secret and the shares are elements of a finite field, FQ. So they have the same size. So it's an ideal secret sharing scheme. So those are some of the basic concepts in secret sharing. So now we look at the connection between secret sharing and cumulative arrays. So we will use cumulative arrays to construct secret sharing schemes. So basically the problem that we're going to consider is, suppose you're given an access structure, gamma. So one of the main questions in secret sharing is, can it be realized by a perfect secret sharing scheme? So is it possible to construct a perfect secret sharing scheme for any access structure gamma? So we will answer that problem. So we will need the following simple threshold scheme, the N out of N threshold scheme. KGH means Karnin, Green, and Hellman. So those three are the ones who first mentioned this scheme. So this one is is similar to my introduction. You divide the secret into N pieces. So that's basically the scheme. So it can be defined over an abelian group. Now, if you have a secret S, so to generate the shares, so the dealer selects n-1 elements of the group, and then computes the following for y sub n. So basically, the secret is the sum of the y sub i's. Now, y sub I is given to participant p sub I. So you can verify that it is an n out of n threshold scheme. So you need all the shares to determine the secret. And if you have less than n shares, you cannot obtain any information about the secret. Okay, so next we define cumulative array. So a cumulative array is the following. We have an access structure gamma, and then we have set X. So it has D elements, and then we have a mapping from the set of participants to the set of subsets of X. So mapping tau from the participants to set of subsets of X, collection of subsets of X. Now, we call this pair tau X a cumulative array if the following condition is satisfied. So we have a set I is in the access structure if and only if this is satisfied. So for each participant in I, so its image under the mapping tau, so if you take the union, it will be the set X. So that is what we call a cumulative array. Now, an example of a cumulative array is the following. So you consider the set of all maximal unauthorized subsets with respect to gamma. So an example will be in the case of the T out of n threshold scheme, you collect all the T minus 1 subsets. So subsets of size T minus 1. Those are the maximal unauthorized subsets. So you can use this to define a cumulative array using the following mapping, tau. So if you remember, tau is the tau is a mapping from P to the collection of subsets of X. So we define tau as follows. So given P sub I, tau of P sub I is the following. So it is the all the T sub j's such that P sub I is not in T sub j. So all the maximal unauthorized subsets not containing P sub I. So that's the mapping tau. So you can verify it is a cumulative array for gamma. So this one was mentioned by Jackson and Martin in 1990. So we have the following theorem. So if you have a monotone access structure, so it can always be realized by a perfect secret sharing scheme. So the existence problem of a perfect secret sharing scheme is solved by these three Japanese researchers. So they proved that there is always a perfect secret sharing scheme for any monotone access structure. So we can discuss the proof of this. So it uses the cumulative array and the n out of n threshold scheme. So suppose we're given an access structure gamma. So our goal is the following. We want to construct a perfect scheme realizing gamma. So suppose we have a cumulative array, tau x, for gamma, so where x is the set. So you can use the previous example as a cumulative array, but there are other examples of cumulative arrays. But you can use that one. Now, so if you have a secret S, the first step is to construct D out of D threshold scheme. So D here is the number of elements of X. So you construct a D out of D threshold scheme for the set X. So you will have D shares out of this scheme. So suppose these are the D shares, V sub 1, V sub 2, V sub 3, and then you distribute them according to the mapping tau. That's how you distribute the shares. So what happens is a participant P sub I will receive the following set of shares. So it will receive all V sub j's such that x sub j is in tau of p sub I, because we distribute according to the cumulative array. So if you take an element of the access structure, so what happens is they will have all these p sub i's by the property of a cumulative array. If a set is in the access structure, so they have all the elements of X. That's the property of a cumulative array. So they can reconstruct the secret because these are the shares of D out of D threshold scheme. So they have all the necessary shares to recover the secret. Now, if a set is not in the access structure, so they will not possess at least one of the P sub I. So they have a missing P sub I. So again, using the D out of D threshold scheme, they cannot obtain any information about the secret. So we have seen that this scheme, so the one I described here, so it realizes the access structure gamma. And you can use it to realize any access structure, given any access structure gamma. So that's the proof of this theorem. Any monotone access structure can be realized by a perfect secret sharing scheme. Okay, so the construction is good because it can be used for any access structure. Okay, but it has one major weakness. The weakness is the size of the shares. So if you look at the size of the shares, usually a participants will get multiple V sub j's. Okay? If you recall the Shamy threshold scheme, the share is just one field element. Now, if you apply this scheme to the threshold scheme, T out of N threshold scheme, what happens is a participant will receive how many shares? If you use the example of a cumulative array I've shown before, a participant will receive n minus 1 taken t minus 1 shares. So it's a large set of shares as compared to the Shamy threshold scheme. Shamy threshold scheme is more efficient for the case of the T out of N threshold structure. So that's one weakness of this construction. So it's very inefficient in general. Okay? So an open problem is the following. It's still, this one is still open. Is to improve on this construction with respect to efficiency. So efficient general construction of secret sharing schemes. So it's still an open problem. And as far as I know, this one is the latest paper to tackle this problem. So it's by Bimel and Peter, secret sharing from robust conditional disclosure of secrets. So it's a very recent paper. So they improve on this construction. Okay, so that's the secret sharing scheme and cumulative arrays. So now we go to the connection between secret sharing and Meteoroids. So Meteoroids are combinatorial objects, so it's used in combinatorics. So I will try to describe the connection between these two. So we start with definition of Meteoroids. So Meteoroid is the following. So you have a finite set Q, and then you have a collection of subsets of Q. So we denote it by I. So a Meteoroid is this pair, Qi. So we denote it by M. And it has the following three properties. So the empty set is in I. Second property is if X is in I and Y is a subset of X, then Y is in I. This one, it reminds of the monotone decreasing property, privacy structure. And then you have this third property. So if X and Y are in I, and the size of X is less than the size of Y, then there exists an element Y in Y but not in X, such that X union Y is in I. Okay? So this is the definition of a Meteoroid. Now, perhaps it will remind you, if you look at the properties, it will remind you of the vector spaces, so linearly independent set. If you have a linearly independent set of vectors, they satisfy these properties. So, actually, Meteoroids were introduced to generalize the concept of linear independence. So, that's why you will see yung similarities dun sa linear independence in vector spaces. Now, some more terminology. So, the sets in I are called independent sets. And then you will see the similar terms in linear algebra. So, a basis of a Meteoroid is a maximal independent set. And then the dependent sets are those that are not independent. And then a circuit is a minimal dependent set. And then we say that a Meteoroid is connected. So if you take any 2 points in the finite set Q, so there exists a circuit containing those 2 points. So perhaps it's better to give an example of a Meteoroid. Okay, so as I said, it's a generalization of the concept of linear independence. So you expect an example of a Meteoroid will come from vector spaces. So suppose you have an m by n matrix over a finite field FQ. So we denote the matrix by A. Now you look at the columns of A. So it has n columns. So those columns will be the elements of the finite set Q. So the finite set Q is the 1 to n, corresponding to the columns of the matrix. And then we define the set I. So there's a mistake here. This should be Q. X should be Q, sorry for that. So define I to be the collection of subsets of Q such that the corresponding columns are linearly independent. So the elements are the columns, and then the independent sets are the linearly independent sets of columns. So you can check, they verify the properties of a Meteoroid. So we call this vector Meteoroid. But take note, you have other examples of Meteoroids that are not from vector spaces. So, but this one is, I choose this example because I guess we can all relate to this example from vector spaces. Now, related to this example is the concept of representability of a Meteoroid. So we say that a Meteoroid is representable over a finite field FQ, or FQ representable if there exists a matrix A over FQ such that M is isomorphic to the vector Meteoroid. So we say a Meteoroid is representable if it is essentially a vector Meteoroid. Now, so what's the connection between Meteoroids and secret sharing? So actually, the connection is on the access structure. So if you look at the access structure of a secret sharing, you can look at it as a Meteoroid. So we have the following. So suppose you have an access structure. So again, access structure are the collection of subsets of participants that can recover the secret. So you can define a Meteoroid on an access structure. So basically, the set Q will be this set. So 0, 1, 2, up to n. So you can just look at this as 1 to n corresponds to the participants, and then 0 corresponds to the dealer. So the finite set will be the dealer and the participants. And then we have this property. So the minimum access structure, this one, the elements are the minimal sets of the access structure. So you can identify the elements of the minimum access structure as circuits of Meteoroid. So circuits are the maximal dependent sets of a Meteoroid. So the minimum access structure will be the circuits containing 0. The circuits of the Meteoroid containing 0. So that's the connection between the access structure and the Meteoroid. So if you look at the minimum access structure, you can interpret the elements as circuits of a Meteoroid. Now, the significance of this connection is that this one is used to characterize ideal access structure. So if you remember, I mentioned that problem. We want to determine the access structure that can be realized by an ideal scheme. Because ideal scheme is the very efficient perfect scheme. So Meteoroids are used to attack that problem. Now, so this definition implies the following. There is a one-to-one correspondence between the minimum access structure and the set of circuits of M containing 0. Okay, so that's basically this one. And then if you have a connected Meteoroid that is appropriate for an access structure, that Meteoroid is unique. So again, this one is the open problem, characterize the ideal access structure. So I will mention some of the classical result on this one. So it's still open, okay? And usually they use Meteoroids to deal with this problem. So we have the following necessary condition given by Brickell and Davenport, 1991. So if an access structure is ideal, then it has an appropriate Meteoroid. Okay? The problem is it's not sufficient. Okay? So this guy proved it's not sufficient. So there is an access structure that has a corresponding Meteoroid, appropriate Meteoroid, but it's not ideal. Okay? So this one is not sufficient. So they also gave a sufficient condition, but it's not necessary. So if you have an access structure gamma, and suppose you have, it has an appropriate Meteoroid M. So if M is representable over some finite field, so this means that M is a vector Meteoroid. You can look at M as a vector Meteoroid. Then gamma is an ideal access structure. So there is an ideal scheme realizing gamma. So this is a sufficient condition. But it's not necessary because there is an access structure such that the appropriate Meteoroid is called the non-Pappus Meteoroid. This one is not representable over any field. But its appropriate Meteoroid is ideal. So it's not a necessary condition. So basically that's the main relation between secret sharing and Meteoroids. Next, we look at the following. So this time we look at the connection between linear secret sharing schemes and another object. called monotone span programs. So this one is from computer science. So this one is used to study linear secret sharing schemes. Okay, so what do we mean by a linear secret sharing scheme? An example of a linear secret sharing scheme is the Shamy threshold scheme. It's linear. So these are some of the properties. So the set of secrets and the set of shares are vector spaces over FQ. Now, the secret is reconstructed as a linear function of the shares. So, or each share is a linear function of the secret. So those are the properties of linear secret sharing schemes. Most of the secret sharing schemes studied are actually linear secret sharing schemes. Now, the significance of a monotone span program is that it is equivalent to a linear secret sharing scheme. So if you study linear secret sharing schemes, one good way to study them is to represent them as monotone span program. Okay, so what is a monotone span program? So it was introduced by these two researchers, 1993. Okay, so again, you have an access structure, set of participants, a monotone span program, it's denoted by this. So it's over a finite field FQ. You have a matrix, and then you have a vector epsilon, and then you have a function phi. So that one is a monotone span program. So now, so M is an L by E matrix over FQ, where E is less than or equal to L. And then the function phi, so it's just a labeling of the rows of M. So if you look at the rows of M, you just assign a label for each row. So that labeling is the function phi. So it's a function from the rows to 1 to N. And then the vector epsilon is, in general, actually it can be any non-zero vector. But usually they use this one, this unit vector. So it's called the target vector. And then the size of the monotone span program M is the number of rows. So going back to the function phi, which label the rows of the matrix. So basically you're assigning, you can think of this function as it assigns one or more rows to a participant. So you're assigning the rows of a matrix to a participant. A participant can have more than one row. So continuing with the property of a monotone span program, so if you have a subset of participants, so if you have a subset of participants, because of this labeling, so they are assigned rows of the matrix. So let M sub A be the restriction of the matrix M to the rows assigned to the members of A. So the rows that they were assigned to. So we say that the monotone span program accepts A. So if the target vector is in the row span of M sub A. So we say that A is not accepted by M. So it means it's not in the row span. So we say that M rejects the subset A. So basically, if you have a subset of participants, we just look at whether the target vector is in the span of M sub A, of the rows corresponding to the participants. So we say that a monotone span program computes the access structure gamma. So if it accepts exactly the authorized subsets. So this theorem So I will describe the correspondence between a monotone span program and a linear secret sharing scheme. So this one is one direction. If you have a monotone span program, you can have a linear secret sharing scheme. So suppose there exists a monotone span program M over FQ that computes an access structure gamma. So then there is a linear secret sharing scheme over FQ realizing the access structure gamma. So I describe the proof. So we're given a monotone span program computing the access structure. So how do we construct a secret sharing scheme? So this is another way to construct a secret sharing scheme. So to share a secret, so the secret is an element of the finite field FQ. So the dealer chooses a vector row, then computes the following. So he uses the matrix and then multiply by this vector. So this vector, the first coordinate is the secret. So you have this, it performs this multiplication. Now the ith coordinate of this vector, that will be the share of this participant. P sub I. So that's basically the linear secret sharing scheme obtained from the monotone span program. Now we continue. So since the monotone span program computes the access structure, so for any authorized set, it means that the target vector is in the span of M sub A. So that's why we have the following property. There exists a recombination vector lambda such that we have this. So the target vector is in the span of M sub A. So because of this property, they can recover the secret. If you look at this one is the dot product. So if you compute the dot product of this, so lambda, the recombination vector, and this one, so it will be equal to the secret. So they can recover the secret S. And then suppose you have a subset of participants that is not in the access structure, so they are not authorized to recover the secret. So by the property of the monotone span program, the target vector is not in the span of M sub B. That's the property of the monotone span program. Perhaps we just go over this one. What happens is they will not obtain any information about the secret using linear algebra. So this is the proof of this theorem. Now the other direction is the following. If you have a linear secret sharing scheme, then you can obtain a monotone span program over FQ that computes the access structure. Okay, but I will not show the proof of this one. It's longer than the first one. Now, a special case of this construction is what we call the vector space construction of secret sharing. So Brickell was the first one to use vector spaces to construct linear secret sharing schemes. Actually, the connection between secret sharing scheme and error correcting codes is it's essentially vector space construction. So it came from this idea by Brickell. So that's the connection between linear secret sharing and monotone span program. Next, we consider another type of secret sharing scheme. It's called ramp secret sharing scheme. This one is an example of a non-perfect scheme. So if you remember, a non-perfect scheme is, it has this property. So again, it's wrong. So the union of the access structure and the privacy structure, so there will be a subset that can obtain partial information about the secret. So that's what we mean by non-perfect. So there exists a subset A of participants that has partial information about the secret. So in terms of entropy, you have the following inequalities. So h of s given s of a is greater than 0 but less than h of s. So they only have partial information. Now, the advantage of a non-perfect scheme is it can be more efficient. Okay, it has less security, but it can be more efficient. So the size of the share can be smaller than the size of the secret. So that's the advantage of a non-perfect scheme. So it was proved, it was given by this theorem, concerning the size of the shares of a non-perfect scheme. So we have the following. So in any non-perfect scheme realizing gamma and delta, so we have the following. Logarithm of the cardinality of S of I. You can look at this as the size of the share. So it can be greater than or equal to this one. Okay? So basically, this theorem says that the size of the share can be smaller than the size of the secret. So RAM schemes are an example of non-perfect secret sharing scheme. So it was introduced by Blackley and Meadows. So a RAM scheme is defined as follows. So we have integers n, t sub 1 and t sub 2 satisfying this. So t sub 1 is less than t sub 2. So a t sub 1, t sub 2 and RAM scheme is a secret sharing scheme realizing this access structure and privacy structure such that these two properties are satisfied. So if you have a subset with size at least t sub 2, it is authorized to recover the secret. And if you have a subset of size at most t minus 1, it will be in the privacy structure, so no information about the secret. So it's an extension of a threshold scheme. Now, we say that a RAM scheme is linear if it satisfies this property. So, if you have a RAM scheme, we have the following. Basically, it says that the size of the share of the participant is at least this value. So it can be bigger. It can be bigger than the. It can be smaller than the size of the secret. So that's the advantage of RAM scheme. And an example of RAM scheme is we modify the Shamir threshold scheme. So the secrets and the shares are elements of FQ. The size Q will be greater than or equal to n plus t sub 2 minus t sub 1. So here the secrets are represented by this element. So S sub 1, S sub 2, S sub t minus 2 minus t sub 1. So those are the secrets. So to share those secrets, the first step is the dealer selects this number of distinct elements from FQ. So n plus t sub 2 minus t sub 1 distinct elements. So we denote by this. And then it chooses t sub 2 elements denoted by the a sub i's from FQ and construct the following polynomial of degree at most t sub 2 minus 1. Okay. Now, the polynomial has the following property. F of c sub I is equal to the S sub I. S sub I will be one of the secrets. One of the secrets. So it's just an extension of the original Shamir threshold scheme. In the original Shamir threshold scheme, if you remember, the secret is the constant term of the polynomial. So it's equal to f of 0. So for if you want to extend to a RAM scheme, the polynomial has this property. So some of its evaluations are equal to the secrets, components of the secret. So f of c sub I is equal to s sub I. So I from 1 to t sub 2 minus t sub 1. And then the share is the same idea. The share of p sub I is given by f of x sub I. So you evaluate the polynomial at x sub I, and then you give it to the participant p sub I. So what happens is if you have at least t sub 2, if you have at least t sub 2 participants, they can reconstruct the polynomial because the degree of the polynomial is at most t sub 2 minus 1. So they can recover the polynomial. So if you remember the property of the RAM scheme, this one, so if you have subsets of size at least t sub 2, they are authorized to recover the secret. And then if you have at most t sub 1 participants, so they will obtain no information about the secret. So same as before. But if you have participants, if you have a subset of participants of size greater than t sub 1 but less than t sub 2, so they will have partial information about the secret. So it's a non-perfect scheme, and it's an example of ramp scheme. Now the information rate is the following. It's the difference between t sub 2 and t sub 1. So it can be greater than 1 because it's a non-perfect scheme. So in this sense, actually, this is an example of an optimal non-perfect scheme. So that's the end of the first part of my talk. Thank you. Are there any questions?
Thank you, Dr. Romar de la Cruz, for the lecture on Introduction to Secret Sharing in the first session. It was a great presentation. The next agenda is coffee break for 30 minutes. We will continue our second session at 11 a.m. with Dr. Romar de la Cruz. Thank you.